Okay, thanks for it.
Yeah, sure. Okay. Uh, Upon this more number of chips were getting up more. So what is the basic no requirement for that? It's a trade-off. Trade-off is nothing but like entering into the market whenever it is whenever it is having more demand. If we have missed out the demand, what we will lose every market money, each penny what we have spent over the chip, like in the design phase, testing phase, and marketing phase, and some on fabrication phase, everything we are going to lose at the penny, like cost size. So the trade-off is the main important thing we need to take in care, and other thing is quality of the chip. So if suppose like if you are developing like 100 chips and you are giving out 90 faulty chips, then what is the use? Like in the market, you can't go with the faulty chips. So making sure uh, the chip which you are fabricating will be a fault free, and you are while having these manufacturing defects, everything you are overcoming that, and you are making sure that chip is nothing have any defect, and that will be work properly, which you have intended. Like if if your chip is working as a communication, so definitely the signals should be properly connected up. They should not be broken in the signal part. So right. So like that, some manufacturing defects, everything will be taken care, so that only we will be deliver most quality chips in the demand market. So that is the basic thing why we are going for DFT. So DFT facilitates us to test the chips in a very less number of time, less cost, comparatively. Like it's not a less cost, but comparatively when it comes to other way of testing the chips over required features. So overcoming those test costs, this DFT facilitates us. So that's why we are going for DFT. DFT, yeah, as you abbreviated, it's a design for testability. So DFT includes a definite set of architecture will be implying on the logic gates, memories, and if we are getting some IPs, so how we are placing up, and how we are controlling the data and pushing the data into the chip, and we are getting out the data, we are getting observe the results, and then compare out like whether it is having some defects, or it is having some issues with the functionality, everything. So this is what we are majorly looking out into the DFT. One is controllability, second one is observability. First, controllability. What is controllability? Is nothing but whatever the required data we want to. Okay. Let's give me an example. Like we are checking out for a fan. What will fan do? It is just like if you switch on the fan, then what it needs to do? It has to be rotate, right? And the second thing, what you can check whether at every regular speed control the fan is working or not. Like 1, 2, 3, up to like 6 or 7, whatever the speed control you have set it. So after that, what we are what we will be testing? Okay, you are continuously running the fan, whether it is getting overheated or not, right? And the fourth thing, and what is the voltage it is taking, whether it is taking more current or something. So these four factors we will be checking out. Okay, so for taking out these four factors, what first factor is what? Whether the power, whenever we are giving out the power, then it is running or not. So what it requires? It requires a power supply. So that is the required input. So that we have to deliver with the DFT architecture, which we are implementing onto the chip. Okay, you can have asked me the question like, okay, already the chip is having some design logic. Why we are adding more logic into the more logic for DFT again. Why we are required that? Can anyone guess the answer? Like Sheikh, Aisha, Ganesh, any answer?
Checking the defaults, sir.
Sorry,
Checking the defaults.
checking the defaults. That is correct, but might be you can tell like like a ranking base. Might be the out of five. Might be it is three or four which you have answered that. I will be looking out for priority one on two answers. Why we are adding more logic instead of having the existing logic? Why we are heading up the more logic pertain to DFT. Any guesses? Aisha, Ganesh? Okay, okay. Usually, the existing logic, what they will be, no, intention of that logic, that will be functionality of the design. Like if you are selecting that chip is going to perform some calculator operations, okay, then the design logic will be exactly looks okay, only calculator operations. If that same chip, if you are using for a computer, like laptop or tablets, so that tablets, those chips will be intended only for the functionality which it can do for those tablet operations or no laptop operations. While here, right, to overcome this, it will be having a huge logic which it has intended for different functionalities. But to get overcome this no data pushing into the logic and getting out the results will be dependables on more gates will be dependable. So we can't assume like this error is because of what we have given and what it has the defect inside that. So to overcome this yeah, this difficulty, what we are giving, the extra architecture we are going to implement in the just to add on to the functional logic which it has designed. So this extra logic, what it helps us to, it will uh, it will helps us to deliver the inputs whichever we require for testing to the logic, and then after getting up this logic, and the patterns or values whatever we have given test vectors, then the corresponding responses will be get observed at the output sides. That is what observability means. So to make it this like controllability over the chip and the getting observability on the results, and to compare out the results to check out like whether the chip is faulty or fault free. So for that reason, we are adding a more some more architecture in while we are getting implementation of scan insertion. So basically, scan insertion is nothing but we are adding extra logic over the functionality of the over the functional logic of the chip. Okay. What is exactly this scan insertion do? It is just like a idea. We will be having the chips, right? So it's just like a controlling the inputs of the various gates, like a flops and latches or muxes, everything that every logic chip or something, right? To we need to able to control the inputs. Like if you are having some set of defined logic, suppose let's take an example with a whiteboard. Yeah. So this is one set of logic, and this is one set of logic, and this is one set of logic we are having in the chip. And this is having the pins to communicate with the other outer world or internally onto the chips onto the SOC. So, okay. And here inside this set of logics, right, it will be having muxes, it will be having latches, buffers, and it will be having mux. So different combi logics it will be having, and this will be having suppose flip flops or registers we call. So every register or every mux or every buffer even, it will be having the inputs and outputs, right? That we are able we need to make that we can able to post the vector value, test vector value. Suppose what is the functionality of the buffer? It is just like giving out the input with the um, more buffer strength, that is driving strength. Suppose like what we are doing, it's a very regular example like what we do. Okay, that a single guy who is having no food for 4 days, and he's trying to lift a weight, and the same guy with the he's having a adequate few food and he's taking all proteins and all, and he's trying to taking a weight lift. Then who will be the who can easily can weight lift? The guy who is taking the like protein food everything in a regular time, right? So that is what the buffer does. It will gives out some drive strength so that it can drive more of the signals. So that's a basic functionality of the buffer, right? So here, just it will drive the input with the more buffer strength, so that it will drive other signals in a more level. So here we need to able to apply the test vectors on the buffer from the top level pins, which we are getting communicated. So for this, we are implementing some scan architecture. Scan architecture is nothing but whatever the okay, and that's will explain more deeply. So that is was the basic idea of the scan, to control the inputs of various gates, flip flops, or buffers, everything, and also the observe the outputs of the internal flops. You understand, like this one, right? This flops outputs. So this we are need to get observed from the outputs. These are the outputs. So this architecture we are going to implement using the scan methodology. And what is this? How it can do? Yeah, this is what it replaces all the selected registers of which we had inside the design with the scan flops. What is scan flops and what is normal flops? Okay. Mm, yeah. Can anyone tell me what is normal flop it will be having? Register. Okay, let us taking assume this is a flop. Can anyone tell me what are the inputs? Hello, guys. Hello, Ganesh, Aisha, Sheikh.
Sir, where you telling, sir?
Yes, sir.
Oh, sorry. Are you able to see my this whiteboard?
No, sir.
No, sir.
Oh, shit, shit.
Jam file is not open.
Okay, okay. Wait, wait, wait. No, all these times I'm explaining with whiteboard. Oh shit. Hmm. Okay. Shit. Whatever I have explained is okay. So okay, let's see. This is what some logic. Okay, now you are able to see.
Yes,
Yes,
What?
sir.
sir.
Okay, let me explain again. This is the logic inside the chip that will be having some. Okay, this is the chip, suppose, and this is the pins you have connecting from the outer world. What we are giving some inputs, clocks, everything. Okay, and inside this logic, what will be inside this logic? Definitely, it's a logic elements, buffers, flops, and might be the muxes, and might be buffers. Okay, and some sort of like AND gates, and this all will be get connected up. Suppose like this, they are connected up. Yeah, like this. Once again, guys. Hello. Hello. Yeah, sorry, guys. Hello.
Yes,
Okay,
sir.
okay, sir.
Yeah, you are able to see, right? Yeah, this is what the scan architecture, what it helps us to do. Like this is what AND gate inputs. Okay, now I want to drive these inputs. Okay, from this. I want to drive this AND gate. What it needs to do, it needs to connect up all this through the functional logic it has, and it will directly depends. on this flop and this flop and this marks, and there it is going for one input. Okay, another it is again, this is one register and this is one again latch, and then it is depends, and then we are trying to pass it to the second vector, and this output is getting observed from here and then here it is. Okay, so to post the value and to check this whether this input is defect free or fault free or not, we are need to depend on the other logic. Okay, from this, whenever we are getting the response from this, right, we can't tell that whether because of this logic it is having the issue or because of this logic it is having the issue. And from that we can't assume that, like, okay, because of this it is, we can't judge it up, okay, this defect is been because of this logic or this logic. Okay, to overcome this difficulty, what we are going to do is we are replacing this functional logic with some set of scan logic. Okay, this scan logic facilitates us to drive these inputs directly like this. And this will be directly like this. If it is it will be getting replaced with a scan flip-flop, register or flops, anything we can. Okay, like this it will helps to know to test over the logic cells like inputs, or and then we will need to get observe the output results from those scan cells, and we are able to drive the inputs through the scan architecture, and we can able to apply the vectors at the input side of the logic cells, and those output responses will be propagated out through the output pins, and directly we are we're getting driven the outputs to the output pins, and there we will be having some comparators or simulated values will be checked out whether it is having a fault free or it is having a, like, uh, it is just like a okay, it is has no issues or something, we can make sure that. Okay, okay, that is what it mentions in the first place. Okay, and the second point is what it is telling, replacing all selected flops with scan flops. What it means? Okay, just tell me, what are the inputs of a flop? Can you, anyone guess?
Scan in and clock.
Yeah, one second. Yeah, tell me.
Scan in and clock.
No, 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 no. It is just normal a flop, normal flop. It's not a scan flop. I'm asking only normal flop. In usual uh, flop, flip flop. If you wants to more understandable, and mostly we will be calling every this we will be calling it as register. This is the usual words we will be, technical words we will be using. We need to know familiar both the technical words, either flop or the registers. Okay, yeah, now tell me, in a normal flop, what are the inputs and what are the outputs, or what are the pins it has? Okay, let me tell that one is data input. What is data? D pin. The other case is output pin.
That is
Output
Q.
pin we can, label it as, sorry, yeah, tell me.
Q.
Hello?
Hello?
Yeah, tell me, Ganesh.
That is Q, that output.
Correct. Q. That usually we represent that label as a Q. 1 second. I'm just having a call. Hello? Yeah, sorry. Hello?
Yes,
Yeah,
sir.
tell me.
Yeah, sorry. So one is the data input. This is input data. Okay. And this is output. And this is clock. Usually we represent, okay, 1 second. This is a clock. And this is a reset pin. These are the basic pins we will be having in the flip-flop. Uh, you understand, right? What is the flip-flop and how it works? The right? Hello?
Yeah, yes.
What you do usually the flip-flop?
Transferring the data, sir.
Transferring the data. That's correct. Okay. Even it will now flop. It's a memory element. It will be memorize the value whatever you are giving. Even it's a memory element. Again, it uh, it will be just transferring the data, correct, and even it will store the value inside this. Okay, and it's how it will stores that basic operation. It depends on the clock signal how we are giving, and this flip flop will be having it two types. Can you tell me how many? What are they?
Q and Q bars.
Sorry,
Q and Q bar.
Q1 Q bar. Q1 Q bar are the just outputs and output inverts. I'm asking. Okay, this is a flip flop, right? There will be two types of flip flop. What are the two types of flip flop? I will give a clue.
SR flip flop, JK flip flop.
Oh, okay, that's a types of flip flop. Um, okay, that is a set reset and JK flip flop. It's a types of flip flop. But in the usual DFT, our technology, we will be using two flip flops, two kinds of flip flops. It based on the clock how we are giving. That is paused flip flop. Do you understand like what is meant by paused flip flop?
Yes, sir.
And second one is, can you tell me?
Negage.
Correct. Okay. And what is paused flip flop? Can you tell me what is paused flip flop?
Positive clock cycles. When
Positive clock cycles. Okay. I am drawing out the clock. Okay. Tell me what is this and what is this? Can you tell me like what is this called and what is this called?
High and low, sir.
High and low. That is correct. But even more technically, like pertaining to DFT, I'm asking.
Rising edge, falling edge, sir.
Correct. That's correct. That's good. Ayush. And see what we are telling. It is rising from 0 and it is rising to 1. So what we are telling, what we will be telling this will be a rising edge. And what are the this edge? What we call it's from the top like a logic 1 or high level. It is going low. What it is going to 0. This is called falling edge. And other name of this rising edge is what? Pause edge. The other name of this falling edge, what we called it as neg edge. Got it? Hello?
Yes, sir.
Yeah. So the representation of pause edge flop and neg edge flop, how it looks is this. This is suppose flop. And basic difference when it is pause edge and when it is neg edge. Suppose I'm telling this is a neg edge flop. Can you tell me like what is the difference between this neg edge and pause edge? Where exactly we will be having this Difference?
Bubbles.
Bubble. Where? Where the bubble?
Arrow mark.
Here. What did that bubble mentioned? What it represents? Sorry?
Negative edge.
Negative edge. Correct. So whatever the clock we are giving, right? That it is a negative edge clock. And here, what we are giving here, it is a positive edge clock. Okay. Now tell me, this is a positive edge clock and this is a negative edge clock. What it means, like how the clock here in the negative edge clock, negative edge flop, where exactly the data will capture. Here the clock pulse. Okay. Now let me erase this one. Okay. Yeah. Now tell me, for this neg edge flop, where the data will be captured? Which edge it will be capturing the data? Hello? Yes, guys. Okay. As you told, like this is the rising edge and this is the falling edge. Correct, right? Whenever we are giving neg edge means that whatever the data we are pushing here at the input level will be taken at this falling edge. Every falling edge data will be captured. I mean, not every falling edge. Once again. Yeah. This falling edge and this again here. One cycle finish. And this. Okay. And here again. On, off, and then again this. Every falling edge, whatever the data, it will be capturing. Okay. Oh, let me ask you this. Okay. This is the data input. Hmm? And this is the clock. Okay. And I am telling this is a negative edge clock. Negative edge flop. Now, can anyone try to tell this what is the output, how it will die? Hello? Guys?
Yes, sir.
Yeah. Can you tell me like how the output will be? Yeah, because why I'm why I'm asking this one is this basic understanding of the flops will be more required in while analyzing or even when we are getting up for the simulations or something, then the basic understanding of the flop is very much required. Then only we can able to see what values, where it is driving, what type of flop, and how and what value it will be driving up, what will be expected output. That and all we can able to understand what is that and what is this, like that. Had you guys gone through this flip flop, and the behavior of the flip flop and how it acts everything? Hello?
No, sir.
No. Okay. Let's make a note of that. Okay. Let me create a note. Behavior of flops and the uh, data analysis. Data. Okay. These are the two things we need to know before we kickstart the scan. That basic understanding of the flops, it will be required. Okay. Okay. Let's start with the understanding of the flop. Okay. Let's take one flip flop. This is the flip flop, and this is the input. As you already told, usually we will be referred that labeled as a D input, that is data input. The output will be Q. Output will be Q, and this clock. Got it? This is the basic architecture, like a reset again. Basic pins and the flop, how it looks like. It's a right now. If you don't have the bubble on the clock path, then it will be saying posits. If you have bubble on the clock path, clock pin, then it will be saying that as a negate. And now what it is, posits flop. Okay, got it?
Yes, sir.
Yeah, because every scan, everything, right? This is the basic element we will be having. Just a basic element we will be requiring for the scan architecture. Okay, this flop only we will be converting that into scan flop. Okay, let's we will be seeing in the upcoming that one. So this is the posits, and what is the negate? In the clock path, if you find any bubble, then that is represents as a negate. Reset Q D and the clock negate. Now let's try to understand the posits flow behavior. So this is the data input what we are trying to give some random values. I am talking about the positive edge flow. Okay, and now I'm applying the clock. How it will be This clock, okay, this is the clock we are giving. What I have told, every data input depends on the clock, the output will be shifted out. That is the basic functionality of the clock, right? But which edge of the clock it will be, data will be captured. That is the main important. What we are targeting is the pause edge flop. Pause edge flop will capture the data at which edge? Hello?
Positive edge.
Positive edge. Where exactly the positive edge? Here, here, where it will come?
Rising edge, sir.
Rising edge. Rising edge is what? From 0 to high. Correct, right? This is what
Yes, sir.
rising edge. So this is what rising edge we will be looking. Okay, now let's see. Here the rising edge. So what is, okay, this is what the rising edge. What it is looking at the data input. What is the value? Okay,
Zero, sir.
okay, this is whenever it is low, it is 0. Whenever it is high, it is 1. Okay, you understand like that. Whenever it is high, right, we usually take 1. Whenever it is low, it will take as a 0. Now see, at this instance of the clock edge, this is the edge. We need to check what is the input we are seeing. What is the input we are seeing here in the data path? It is
Zero.
0. Correct. So now it starts with this. Okay. Here, this is the clock. This is the clock edge. We are trying to get the data here. Okay. What it is? It's a 0. Okay. Let's keep on. Whatever the data which looks at this edge will continue up to this cycle. What is cycle?
1 bit, sir.
Sorry, what is one clock cycle? Hello?
One rising edge to another rising edge.
Not exactly rising edge. It's called T on plus T off. T on is what? Timing on time and off time. Okay, let's see here. Okay, this is what we call it as a on time. T on, and this is what we call T off. This represents a cycle. Got it?
Yes, sir.
So this part, this is called T on. T on is the time which the clock cycle is at the high state. This is on state, on, and this is off. The clock which it is here, and when it comes this one, right? This total up to from here up to next rising edge. This is called a one cycle. Got it? Everyone understand? Hello? Guys? Hello?
Yes, sir.
Yeah, everyone understand, right? What is one cycle? It is T on and T off. So what is T on? It is keeping the cycle like a clock signal. It is at the high level. T off is at the logic 0 level, logic 1 level. This totally represents one cycle. Okay.
Okay, sir.
Yeah. Now tell me how many cycles are there here? Yeah. This is a positive flop. Now tell me how many cycles are there?
Five, sir.
5. Okay. Let me give a control. If anyone wants to try, like where it is, so where are the controls? Control is not there. Got it. Gotten. Sorry. Uh, not able to control. Okay, let's see. Yeah. Tell me where from where to where I need to check the cycle. Hello.
Time on, time off.
Time on, time off is common. Like this is time on, this is time on. This is off, 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 off. But I'm referring the positive flop. From where to where I need to take it as a cycle. Yeah, tell me. Hello? Hello?
Yes, sir.
Yeah, tell me from where to where I need to take the clock cycle. This is one rising edge.
1, 2.
This is one rising edge. This is one rising edge. This is one rising edge. And this is one rising edge. Now,
That's
I
five.
will, sorry, yeah, tell me.
5 circles, sir.
5 cycles, right? This is 1. And this is 2. And this is 3. And this is 4. And this is 5. You understand, right? How the clock cycles will be calculated.
Yes, sir.
Hmm. Now, can anyone try how the negate flop? will be calculated, the clocks. Let me try this. Now tell me how many cycles are there for the negative flop and how I can calculate them. Can anyone? Aisha, Sheikh, Ganesh? Just assume. Let's be an interactive session so that I can understand at what level you are understanding my words, and if you are not able to approach that, then I will try in a different way. That's why I'm asking you, like, try it. Okay.
5, sir.
5. Okay. Tell me from where I need to get it considered. It's a negative flop. So which edge I need to take in?
Second.
Sorry?
It's sir.
Falling edge. Correct. Falling edge is what? From the logic high level, it is going low. That is what we need to check. Okay, this is falling edge. 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 And this is falling edge. Got it? How many cycles are there now? How we can calculate? So whenever you start the falling edge, right, you need to consider this one. This falling edge to next falling edge. This represents a cycle. This is one cycle. And from here to here, this represents second cycle. Sorry. And from here to here, this represents third cycle. This represents fourth cycle. Five. Okay. So this represents totally of 5 cycles. Got it?
Yes, sir.
Yeah. So, yeah, 1 second. Let me take it. Sorry. Yeah. So these are the 5 considered negate cycles. Okay. You understand how to measure the cycles?
Yes, sir.
And here, right, whatever I have mentioned, this T on, T off, we call this is having duty cycle. Just one technical word we need to remember. Duty cycle represents what is the T on. How much time the clock signal is at the high, logic high level. What is that is called duty cycle. I will discuss more on the duty cycle in upcoming sessions. Okay. Right now, let's keep a stick. What is the flop? What is the inputs? And what is the clock? And what type of flops are there? First is positive flop and negative flop. So these for positive flop and negative flop, what is the basic difference? The clock will be having a inverted clock. So this bubble, what it means? This is a clock, right? This will be having a clock. This negative flop, what it will be having? Negative of the clock bar. Okay. Hello.
Okay, sir.
Understand? Okay. So that is what the basic difference of that. And now how we need to take that representation of the clock is from rising, if it is a posit, from rising edge to next rising edge. Up to that, the cycle will be calculated. So type one cycle will be what it contains. One is T on and another is T off. That is the on time and off time. Or on time is what? The signal is at the logic high level is called on time. The signal at the logic low level is called off time. So one clock cycle is T on and T off. Okay. And so other case is what we already discussed, this duty cycle. Duty cycle is what? The logic which it is having at the logic high level, how much time it is at the high level is called duty cycle. That we'll later discuss. Okay, coming back to the previous question. How the behavior of the output. This is still pending, right? Now tell me, like in the positive flop, where we will be looking the data. Hello?
At rising edge, sir.
Rising edge, correct, super. So this rising edge, we need to check what is the input at the D. Okay. Now tell me, for this first clock cycle, what is the input we are seeing at the D?
0.
0, correct. So whatever it has looked it has looked at the data input at this rising edge, it will be carried up to one clock cycle. Got it? So
Yes, sir.
here it is seeing 0 as the input. So this total one cycle, it will be having the value of 0. Okay. Now, see, this is the second cycle we are looking. Correct, right? So here, this is one rising edge. Here, what we are seeing. Okay, let's keep this make clean for you. Okay. This is the next cycle we are looking. So what is the data at the input level? What's the data at the input level?
1.
1. Now, at this time, it will go to 1. How much time it will be 1? This 1 will be stay at how many cycles? How much time?
1 cycles.
One cycle. One cycle is what? Up to next rising edge. Okay. Now we will be third cycle. So third rising edge, we came across. So what we need to observe here. Now, what we are seeing at the day input or the third cycle is
0.
0. Correct. And now, how much time this 0 will get considered? One cycle. Correct, right? Up to this. Correct, right?
Yes, sir.
Up to here. Now, we come across fourth cycle. Let's see. This fourth cycle, what we are seeing here at the input, it is logic high. What it is? 1. So the output will be 1. Up to what? Up to next rising edge. So now tell me, like here, for this rising edge, what value it is seeing at the input level? 1, right?
Yes, sir.
So this 1 will keeps holding up to next cycle. Now we come for sixth cycle. Okay. Now see, at this sixth cycle, sixth rising edge, what value we are observing at the D input? It's 0. So now it comes to 0. And how much time it will be up to next cycle? Now observe for the seventh cycle. See how much, what is the value it is saying? 1. How much time? 1. And now it is capturing 1. And now for this cycle, it is 0. Did you get the cue? You understand how to capture the values?
Yes, sir.
Everyone? Sheikh,
Yes, sir.
Aisha, and Sheikh Jeff. Okay. By the way, like Ganesh, Aisha, and can I call you Jeffrullah or Sheikh? Hello?
Yes, sir. Understands.
Yeah, no. How can I call you? Like Jeffrullah?
Sir, any name, sir.
Okay. Okay, sure. Yeah. So you understand, right? Like how to capture the values at each clock cycles and looking at the data input. Okay.
Yes, sir.
Yeah. So this is the positive edge clock. If we are considered negative edge clock, how we will be taking? Let's see. And this is the clock. Now tell me how I can, okay, this is what negates. Okay, this is what negates. Now let's capture the value at the output for this negative edge flop. Now tell me where and all I need to capture the value. Yeah, tell me where.
Rising it, falling it's.
Falling. Okay, this is clock bar. Okay, for you just better understanding, I'm putting that as a clock bar. But in usual cases, there should not be any clock negative or something like that. It just says a clock, and you need to understand like whether it is a negative flop or it is a positive flop. Based on that, the clock will be the capture the data. So now, okay, this is a negative flop. So where we need to capture at the falling edge. Correct, right?
Yes, sir.
What is the falling edge? From logic high to low. Wherever it is going from logic high to low, that is the falling edge. How many falling edges are there? Understand? How to mark first. Okay. Hello, guys.
Yes, sir.
Yeah. So now tell me, the Q for the first clock cycle means what here? From first falling edge to next falling edge. Now tell me what value I need to capture here. The Q. What value it will come?
0, sir.
Correct. 0. Why? Because at the falling edge, we are seeing 0 at the data input. So it will be 0. Up to what? Up to next falling edge. Got it. Okay. Now tell me what we need to capture. The next falling edge we got. And now we need to see what is the value it is seeing at the data input. What value it is seeing? Logic high. High is what is 1. And how much time it will be logic high up to next falling edge. Now it comes to third cycle and needs to observe at the what value it is seeing at the data input. It is looking 0. So it will go low until what? Next cycle. Now this is the fourth cycle, fourth falling edge. So fourth falling edge, what it is seeing? High. And then again, the fifth falling edge, it is seeing 0. And now, what it is at the sixth cycle? It is logic high. Logic high is what? High. Up to what? Next cycle. Where it is still, it is high. So, how the output looks like? This. Got it? Do you understand that?
Yes, sir.
Okay. Mm, so, and one more case it will be. Uh, did anyone know what is latch and what is flip flop? Or else, no, let's not go through latch. Let's keep it aside. Afterwards, we can talk about the latch. Let's first have a basic understanding of flop, how it works. Did you got what is the flop? Now tell me what and all we have checked first on the flops. So what is the first thing we have checked about the flop? The inputs or ports, all the input and output ports. Second thing is how the clock behavior is. Like posits or negates. Third is data capturing with respect to clock. These 3 points we just gone through to the different phases in posit flop and how it will looks like, and negative flop how it looks like. Okay. Okay, guys.
Okay, sir.
Yeah. So apart from this, we need to have a basic understand of clock on this. Okay. Let's talk about then latch, because again this basic element will be required. What is latch and what is flop? Okay, let's say this is a flop and this is a latch. What is basic difference between the flop and the latch? Can you tell me? Everything looks similar. Okay. So data input, clock input, reset input, output, everything looks similar. Flop and the latch. So where exactly the difference will be? Can you guys?
Inputs are different, sir.
Inputs are different. Like inputs are same. The flop looks okay. This is data input. This is output, which is Q, and this is clock, and this is the reset, and this is also same. This is D input, Q output, the clock. Sorry. Oh yeah, clock and the reset. All are same. So where exactly the difference will be? The to the flop and to the clock. Sorry, latch. Did you guys ever heard like a edge triggering and level triggering? Hello? Can you have you came across this edge triggering and level triggering?
Little bit understandings.
So you know. Okay, tell me like what you understand from edge triggering and what is you understand from level triggering. Because whatever I have explained about the flop, right? From that we can try to grab out what is left level triggering, what is edge triggering. Okay, let me explain. First, edge triggering. Edge triggering. Okay. So, what is edge triggering? What the values at the data will be captured at the edge of the clock, which is clocking rising edge or the flow falling edge. It will just check at that instance, very like where it is falling, right? This instance only it will check for the data input. What is the data at the data? Sorry, D input. Just at the instance, like this. Just at the instant, at this time instant where it is falling edge. If it is positive edge flop, then where it is rising edge, at that instance only it will be checking out like this. Here, like this. That instant it will check for the data and that data will be captured out. Whereas level triggered, whereas level triggering, how it looks like this. Suppose this is the D and clock input I am giving. This is the clock. Now, who better understands for the edge triggering how the outputs will be behavior. First, edge. Let's represent EDG. This is the positive flop, and what is where we will be checking at the rising edge, right? Hello. Hello, guys.
Yes, sir.
Yeah. So at the rising edge, we will be checking the clock. Sorry, data. Correct, right? Only
Sure.
at this instant. This and this and this and this and this and this. Got it? 1, 2, 3, 5, 6. So this is where the data will be get captured. Okay, let's capture here. This is the Q edge. Okay, edge triggering output I am capturing. What is the value? Oh, it is 0. Oh, sorry, it is 1. It is looking. Okay, keep 1 for full cycle. Now it is looking 0, 0, full cycle. Now see, it is seeing 1, 1 full cycle. Now it is looking for 0. Now it is looking for 1. On what, up to what? Here on what it is looking? 1 again. And where here it is looking 1. Keep 1. This is what edge triggering. What just observe what is the word I am using. Edge. Edge is what? Clock edge. Clock edge is what? Rising edge or falling edge. This is what the rising edge, and where we are getting the capture at the output. Now we will be going to the level triggering. Level triggering what? Say now. Now let's understand what is level triggering. Level is what? Level 0 or level 1. Level 0 is what? Which whenever the signal is at the high level, it is called level 1. Whenever it is the signal, it's a low, it's a 0 level, then what it is called? It's a level 0. Level 1 and level 0. That here now, how the data will be captured. See, this is the clock, and this is the again like edge we had. It's a positive level and negative level. It will be there. Let's take a example first. Positive level. Positive level is what? Positive level is what the data will be captured whenever the clock is at the high. Whatever the clock, it is high. It is high. The T on, what it is called. Up to this time, whatever the data it is seeing in the data input, it will capture. Now I will show you. Okay, for this one, for this is positive level, right? Positive level is what? Where the T on. How much time it is at the logic high level. So it will start observing from here to here. What is the value it is looking? It is logic 1. And now here up to high level, up to the T on state, the whatever the D input it is there, that will be captured. Now what about the negative off T off state, negative level? What it will go? Whatever the positive level it has captured, that will get continuous until next rising edge. Okay. Now next T on cycle, up to that it will be get continued. Now see here, this is what T on, this is logic high level, this is logic level high. So now the data what it is seeing at the D input is 0. Now it is 0. And see, within this only, somewhere in the middle of the logic, in the middle of this T on, the data input is what it is going high. Okay. Somewhere it middle of the T on state itself. So until that, like this. Until that, it will be 0. And this is what? It is looking high. High means 1. Up to what level it will go? Okay, this is positive level, right? Up to this we need to check. Okay, this is 1. And now it comes to negative, T off state. T off state, what it will do, whatever the T on state, whatever the value is there, that will get considered up to next positive level. Are you guys following up?
Yes, sir.
Positive level is what and negative level is what, and how the data is capturing. Okay. Okay, let's take this one. Okay, so here until next no rising edge, or until T on, next T on, the data will be 1 only. Now again, what is the up to this time? What is the value of the D input? It is still on up until this cycle. And now it comes T off. What in the T off state, what it will do? Whatever the T on state value it has taken, the last value, it will be get continued until the next T on cycle. Now this T on cycle, what it has observed? 0. So it will be going 0, and until this one, still it is 0 only. So the T off state also, it will go 0. Now we came across like a fourth T on state. Here, what here? See, there is a variances in the data input. Until this, it is logic 1. And within this cycle, this one, see, here it is changing within the positive cycle only. It is logic 0. So how we need to take the value? Okay, here it starts. Here it is looking 1. So it's go high until what? Where? See, at this level, we are again seeing logic 0 value. So until that, it will be 1. And here, whenever the T on state is still on, the data is changing from 1 to 0. So what it will do? It will capture that. It will capture 1 to 0. And now, how much time it will be until this? Now, okay. Now, until that, it comes 0. And in this T off state, what value it has to be propagated? whatever the t on, like a last value is what, 0. So until that 0 will be propagated out. See, now it comes the third, like a fifth cycle, fifth level t on. What it is looking, it is 1. So 1 up to what, until this t on. T on is what, here, this, and this is t off. T off, what it is looking, it will be continue whatever the t on cycle until next level high. So still it is high. See how edge triggering works and how level triggering works. The same inputs, D input, clock input, everything will be similar. Everything will be similar. D, Q, clock, and latch, this reset, everything. But flop will be having like this, which is represents edge, and latch will be just like a clock connection. That's it. Nothing. This bubble and all, everything, it should not be there. Like this, it will not be. Like this will not be there for the latch. What it represents is just like a level. Whatever, whenever is the logic high, whatever the data is there, that will propagate to output. Whereas here in the flop, right, at the clock edge, particularly to that instant, only to this instant, whatever it is seeing at the data input, that data input only will be captured. Whereas the level trigger, whatever the data it is seeing at the this level, like, let's not touch that. Yeah, until this t on state, whatever the data it is seeing, that will be propagated out as the output. Okay. Hello. Hello. Yeah.
Yes, sir.
So if suppose the data is changing within this t on, if suppose, okay, let's see here itself. Let's draw like this. See, within this t on state itself, data, how it is changing, it is changing from 1, and then it is going to 0, and then again it is keep on at the 1 for some time. So for this logic t on, what value it will be observing at the output? Okay, here only that need to get start with the output observation. So for this t on, the logic at the data input is 1. So we are keeping 1. And now see at this level, until this level, the value is 1. And now here this value data input is going 0. Still the t on period is on only. Still the data is we need to observe it, what it is, 0. So now this data input, what it is observing at this instance, we are need to 0 until what, until the t on ends. So up to here it is ending. So this is 0. And for this t off state, what is the value? The last value is what, 0. So it continues. You understand what is edge triggering or what is level triggering?
Yes, sir.
You mean like you got the data, like data how need to capture at how for the flops and the under the latches. Guys,
Understand,
yeah,
sir.
okay. So this is what the basic difference between the edge triggering and the level triggering. So edge triggering is what we call a flop. Whenever it is a level triggering, then it is called it's a latch. Again, as we have the flop, it will be having two types, right? Posits. Second is negate. Similarly, for latch also, it will be having positive level. Second is negative level. Negative level, what it represents? Can you guess? Hello?
Yes, sir.
What is meant by negative level? Suppose this is a clock and we are trying to check for the level triggering. Now tell me what is the positive level and what is the negative level? What is this? Okay, this is the clock. Suppose what we call positive level is whenever the clock signal is at the high level, that represents it's a positive level. So where the data we need to see throughout the this logic high. This is called T on, right? Correct, right? Hello?
Yes, sir.
Yes.
Correct, sir.
Yeah. So this T on period, what we called it as a positive level. And the T off, whatever that logic zero level. This T off, we called it as a negative. Like whenever this negative level means the data needs to be captured in the T off state. Okay. How it looks like positive level, how it looks, and negative level, how it looks. This is a latch, suppose, and this is the inputs. Suppose this is a positive and this is a negative latch. What is the difference? This is D, everything Q. Everything looks similar. D. And this is clock. And this is clock. This is reset. And this is reset. And if this is a positive edge flop, positive latch, then the clock signal will be directly driven to this the representation. Whenever the negative latch it is there, then there will be a bubble at the clock path. Okay. This is representation of a positive latch and negative latch. Okay. Positive latch where the data will be captured whenever the clock signal is high. Negative latch where the data will be captured whenever the clock is at the low level. Got it? Which represents T on. This represents T off. Okay, right?
Okay, sir.
Did you got?
Yes, sir.
Yeah. So this is basic understand of what is flop and what is latch, and again inside that flop and latch, the further classification: positive edge flop, negative edge flop, positive level flop, positive level latch, and negative latch. So how it will be having in the basic behavior of the edge, positive edge, how it is behaving, and positive level, how it is behaving. So let's stick to this as of now. We'll move on to next topics like a how further, like after getting understanding on the latch and the flop, we'll later on we will move directly to the scan flop and how it looks, normal flop how it looks, then when it converts to scan flop how it looks. Okay, so this is the basic understanding of the flop and the latch. uh, for today's session, just get over view of this what is flop and how the behavior is, and how the latches or how the behavior of the latches. So just go through it on this yeah, on this concept flop and the latch, how and the waveforms which we had captured, right? Like this, the data at this cycle, this clock cycle, how the data is, and how the data will be captured at the negative edge. So if it is negative level, then how the I will try to give out some no, some set basic work for how the flop it will looks like for a different set of inputs, and the same set of inputs how the latch behaves. That I will try to give some workouts. Just try to see how it will get the data at the output for positive edge and negative edge, positive level and negative level. Okay. Okay, guys.
Okay, sir.
We'll